Hey everyone, so today's topic is going to be electrostatic potential energy. Okay, so this is very much comparable to gravitational potential energy. So let's go ahead and get started over there, and that way we can transfer over to electric potential energy later, okay? So let's, just background history. What is potential energy? Okay, what we have right here. So potential energy, we're going to define that as, or we're going to write it down as PE. It's defined as mass times height times acceleration, okay? So in the majority of the cases that you usually work with, acceleration is treated as gravity because, that's Earth's acceleration, which is a representation of the little trees that we have here, okay? And that's the formula for potential energy, okay? Now, as you may remember, potential energy is the energy that is stored within something. So for example, let's say that we have this ball here, okay? So this ball is above Earth's surface, right? Which is what we have over here. So if this ball were to fall, the energy equivalent to it falling, which is kinetic energy, if you remember, is all stored up here, which is what we call potential energy, okay? Another way of looking at it is how much work does it take to move an object from, let's say, I don't know, imagine that the ball was down here. How much it takes to move an object from a height that is equal to 0, okay, to x height, okay? That's another way of looking at it. How much work does it take? Because that's the kinetic energy, and when it's up here, it's transferred to potential energy, okay? So that's just another way of looking at it, okay? How much work, I'm actually gonna write that down. How much work, okay, does it take to move an object from A to B, okay? I'm gonna put that in a little square over here. Okay. All right, and that's actually a term that is used a lot in physics, work. Now, just in case you don't remember, the formula for work is work, which is W, is force, okay, times displacement, okay? Now, also, another formula that you probably have heard of before is force equals mass times acceleration. So if you see this F here, this one over here, can actually be replaced by mass times acceleration. So we have work equals mass times acceleration times distance, okay? And this is here where we can see the relationship in between work over here and potential energy. Because if you look at it, we have mass right here, height and displacement, and acceleration in both. Okay? So that's actually why we can see that the formula for work is actually basically the same as the one for potential energy. Okay? This is just so that it's a lot easier to understand the relationship. And now that you understand the gravitational potential energy, we can go ahead and transfer over to the electric potential energy, okay? So let me go ahead and erase this, okay? Just a little bit of a clutter over here. I'm gonna leave the formula for potential energy just for reference, okay? But I'm gonna go ahead and erase, oops, my bad. I'll write it down in a second. Okay. So once again, potential, actually let me write it just a bit of both. Potential energy equals mass times height times acceleration. Okay. So let's say, I hope you paid attention to previous videos, that we have a constant uniform electric field, okay? So I'm just gonna write that down as basically a line, okay? And let's say that this electric field is positive, okay? So I'm gonna go ahead and write down some positive signs, okay? And this is uniformly within the entire electric field. Okay? It expands infinitely in all directions, okay? Now, if we were to have positive charges within that field, this would go away from the field and it would point upwards. You agree? So we have here what is basically the direction of the electric field, okay? Just gonna write a few more arrows, just so you get an idea, okay? Now, let's give a hypothetical strength to this electric field, okay? Let's say 10, okay? So the electric field would have, there we go. So the electric field, so we're gonna write that down as E vector, okay? That would equal 10 newtons, okay, per coulombs, which is basically the force per charge, okay? So now let's say that we have a point charge of 3 coulombs, okay? And that is within this field, okay? So I don't know, let me go ahead and write it down somewhere here. Okay, so this is a positive charge. Okay, and this has a charge of 3 coulombs. Okay, actually, let me go ahead and write it down a little bit more in the center, just so it doesn't get cluttered up in here. All right, and this is 3 coulombs. Okay. Okay, and it is at X height. Okay, so it has a certain height here. Let me erase this. And this is equal to H, okay? Now, 3 coulombs is a massive charge, but this is just hypothetical, okay? How much work would it take for this charge, this one right here, to travel, I don't know, let's say 5 meters, okay? How much work for the charge, we're just gonna write that down as, I don't know, Q, to travel 5 meters. Okay? Well, first we would have to see how much force is being applied to that charge in this specific spot. Okay? So the way in which we do that is because the electric field is constant in this case, so just because a source is here doesn't mean that here the electric field is weaker, okay? We're gonna assume that the electric field is constant, okay? So the way in which we do this is the electric field is equal to 10 newtons per coulomb, which we have here. And the charge is of 3 coulombs, which is what we have here, okay? So the way in which you do this is we multiply the charge and the electric field. So 10 times 3 equals 30 newtons, okay? Because the coulombs here and the coulombs here, they cancel out, so we're left with newtons, okay? And that would be the upward force applied to that charge in that specific point, okay? Because once again, we have here the electric field, which is this little green arrow, okay? That's pushing upward on the charge. And because the charge is positive, it's also going away from the source, which is this this big blue line, okay? So we multiply those and we're left with 30 newtons, okay? Now, to be able to push that charge downwards, okay? So this charge, imagine that we want it to go down, in a straight line, We want it to go down, okay? So we would basically have to apply an equal force of the 30 newtons downwards and, just a little bit more so that we're actually able to move it downwards. If not, it would just cancel out, okay? So let's say that you applied those 30 newtons downward, okay? A distance of 5 meters, which is what we have as the theoretical height, okay? And if you remember, work is just force times displacement, okay? So that would be that the total force, which is 30 newtons, okay? That would be times 5, which is the height. Let me actually go ahead and replace this h for 5 meters, okay? So that would leave us with, so we have the 30 newtons times 5 meters, okay? And that would leave us with 150 newtons per meters, which is basically just equal to 150 joules, okay? Because that is the unit for work, okay? So now that would be the potential energy for that charge relative to the initial position, okay? So this initial charge right here, relative to this initial position, let's say. So if we were to move this down, let me go ahead and draw another. Let's say we move this down right over here, okay? Those are the 5 meters, okay? We went ahead and pushed this charge down, all the way down here. So that was 5 meters, and now it would have a potential energy of 150 joules, okay? Now, let me write it out just so it's a bit more clear. We have the first initial charge right here, okay? I'm just gonna go ahead and repeat this, okay? And we have the first initial charge right here, okay? And down here is the second charge. Now, the work needed to move that charge is 150 joules, okay? Which is where we have right here, okay? And that is the total potential energy that is stored in the charge, okay? Remember this, charge 2 is relative to charge 1, okay? So potential energy with charge 2, being relative to charge 1, okay? And that's equal to 150 joules, okay? It's very important to include relativity, as that gives you a sense of where exactly you're going to be giving the reference from, okay? So here, for example, we know that the charge 2 is relative to charge 1, okay? Now, let's just say, it's not really in this video supposed to be included, but what if we want to talk a little bit about kinetic energy, okay? So let me go ahead and erase a little bit. So I'm gonna go ahead and erase this just to make a little bit of space, okay? So let's say that this charge over here has a mass of, let's say, 2 kilograms, okay? And if we let this charge go, this charge over here, okay? So let's say it has a mass of 2 kilograms, and if we let that charge go, we aren't applying any force onto it, but because it's at the bottom here, it's going to be able to expand upwards, okay? Or it's gonna go upwards, So it's full of that potential energy, 150 joules to be exact, and it's going to go upwards at a force of 30 newtons, which is what we previously knew, okay? So we have the 150 joules being equal, just another formula. 150 joules is equal to 1/2 of mass times velocity squared, okay? So mass is 2 kilograms, okay? So we just pass this 2 over here, so we have 300 joules equals 2 kilograms, okay? So now we divide this over here, and we're left with 150 equals velocity squared, okay? So we get this square root, and we're left with velocity equals, what's the square root of 150? I think it's 12.2 something, okay? Meters per second. All right? So once it gets to the point of the initial position, so we have this charge right here, okay? Once it gets over here, it's going to be going at 12.2 something meters per second. Okay, so it's going to be going at that speed. And, you know, I'm just rambling on just a little bit. But well, actually, we'll go over that in a separate video. But that's just so you get an idea of how this information can actually be really useful, okay? So just to be clear, okay, electrostatic potential energy, very similar to gravitational potential energy, okay? You know, the relationship between work and potential energy and, you know, what we went over in the video, okay? So yeah, once again, I'm just going to write down the formula for potential energy. Oh, it's right over here. Okay. And the formula for work. Okay. So work equals, oh, my bad. Work equals force times displacement. Okay. And the relationship between this. Okay. The force and mass and acceleration. Okay, and yeah, that's pretty much it, guys, okay? So please do like the video and subscribe to our channel so that way you can help support us. And feel free to leave any comment or any recommendation on how we can improve these videos and help you guys learn and help us all grow, okay? Thank you.